Hello everyone, I'm Faisal Etaodia, and in this video you will learn how to create a scene for the Sionna ray tracer, that is Sionna RT, using Blender and OpenStreetMap. The outline of this video is as follows. First, we will see how to import the geometry of a real-world environment in Blender using OpenStreetMap, and assign materials to the different objects forming the scene. Then, we will learn how to export the scene as a Mitsuba scene, and then import it in Sionna RT. Finally, we will see how to compute coverage maps and propagation paths between a transmitter and a receiver, and visualize them in a notebook. To reproduce what you will see in this video, you will need Sionna 0.14 or later, Blender 3, as well as two add-ons for Blender, Blender OSM to import real-world geometries in Blender, OSM stands for OpenStreetMap, and Mitsuba Blender to export and import Mitsuba scenes. You will also need Jupyter for interactive visualization. Let's now learn how to create scenes for Sionna RT using Blender and OpenStreetMap. The main tool we will use to import scene geometries from OpenStreetMap is Blender. The first thing to do is therefore to install Blender, which can be downloaded from the project website. As you can see, Blender is available for all major operating systems. We used Blender 3.3.1 for this video. We will also need two add-ons of Blender. The first one is to export and import a Mitsuba scene, which is the file format supported by Sionna. It can be downloaded using the link available on the GitHub repository of Mitsuba Blender. We used Mitsuba Blender 0.1 for this video. The second add-on we will need is Blender OSM, which we will use to download geometries of cities or any real-world environment in Blender. To download it, just use the link available on the GitHub repositories of Blender OSM. We used Blender OSM 2.6.5 for this video. Once we are all set, that is, once we have installed Blender and its two add-ons, we can start importing real-world geometries using OpenStreetMap. We'll import a small part of the city of Paris in this case. We start by removing these three objects that Blender adds by default to the scene. To do that, let's go here on this view, select the three items, do a right click, and then click on delete. Once this is done, let's open the sidebar by clicking on this small arrow here. As we can see, we have a few tabs available, and if the Blender OSM add-on was correctly installed and is enabled, it should be available here. OSM stands for OpenStreetMap. Let's click on it, and then the first thing we will do is disable everything but buildings, meaning that we don't want to import anything else but the buildings from OpenStreetMap to simplify the geometry. Next, we also don't want to import everything as a single object, and the reason is that we want to be able to assign different radio materials to the different objects in the scene. Once this is done, let's click on Select here, which should take you to your browser and open OpenStreetMap. In OpenStreetMap, you can then select the area you want to import. In this case, we will focus on Paris. And for example, we want to import this area here. So once you are on the area that you want to import, click on the Show Selection Rectangle button, which opens this rectangle that allows you to precisely select the area you want to import in Blender. So for example, let's focus on this part here. We'll choose a small area to speed things up for this video. Once we have precisely selected the range of coordinates we want to import in Blender, click on Copy, and then go back in Blender and click on Paste here. Clicking on Paste copies the range of coordinates you have selected on OpenStreetMap right here. And once this is done, just click on Import. Importing the geometries from OpenStreetMap can take up to a few minutes, depending on the size of the area you have selected in OpenStreetMap. Once this is done, as you can see, the objects pop in the scene. And we can zoom out to view the buildings we have imported. If you want to disable this raise pattern on the ground, go here, then uncheck the box relationship lines. As you can see, we have imported the buildings from OpenStreetMap, but there is no grounds. So we'll add a plane to model the ground. To do that, ensure that you are in the object mode and then click on add, then mesh, then plane. And as you can see, this adds a small plane at the origin. It's actually a small square of size 2 by 2 meters. So let's scale it up to make it cover the entire scene. To do that, we can go here on the properties of the objects, object properties, and here let's scale it up to, for example, 200 by 200 meters. As you can see, this is now maybe even slightly too big for the scene we have. So we can precisely adjust the scaling of the objects by selecting the scale tool here. And when clicking on scale here, we have this, it opens this small frame that we can use to precisely adjust the scaling of the objects along the 3 axes, X, Y, and Z. We can also translate the object by selecting the move tool here and then translate it, for example, to center it on the scene we have imported. Okay. Once this is done, the geometry of our scene is set. Once the geometry is set, we need to assign radio materials to the different elements that make the scene. By elements, I mean objects. Let's start with the ground plane. We first select the ground plane here, and then go on the Material Properties tab. As we can see, there is currently no material created for this ground plane. So let's create one by clicking on the New button. Blender creates a default material with a default name and some default properties for rendering. These properties here are for rendering. One thing quite important is that Sionna uses the name of the material that is assigned to an object to identify the radio material that will be assigned to this object for simulation of wireless propagation. That is, the name of the material here that we put in here must match a radio material defined in Sionna. If we look at the Sionna documentation for the radio materials, we can see that there are a few radio materials that are baked in Sionna. Actually, all the ITU materials are baked in Sionna. A radio material is identified by its name, and every radio material corresponds to electromagnetic EM properties that are used for wireless propagation, for the simulation of wireless propagation. So for example, if we want to use ITU concrete for the ground plane, we just need to type in ITU concrete here. Let's do it. Then, when loading the scene, Sionna will use the properties of ITU concrete to simulate the interaction of electromagnetic wave with the ground plane. Notice that it is also possible to create custom radio material in the Python script that we will see later. When we create in Python a custom radio material, we need to give a name to the radio material. And if in Blender we set the name of a material to be the same name, for example, if we name a material in Blender my material, and if then we create a radio material as shown in this code, then the radio material we have created will be used to simulate radio propagation for the object that was assigned a material with this name. But for this example, let's use only the radio materials that are baked in Sionna, that is the ITU materials. Once we have set the name of the material, we can also define properties for its rendering, that is visualization. For example, let's use a simple diffuse BSDF, and then let's set the color to a different value. Notice that these properties will also be used in Sionna by Sionna for rendering, that is for visualization. Once we have set the radio material for the ground plane, let's do the same for the other elements of the scene, that is the buildings that were imported from OpenStreetMap. We first unroll the list of objects, and for this scene, we can see that all the objects in the scene, all the buildings, share the same two materials. A material called wall for the walls and a material called roof for the roof. If we just rename these two materials for one element, it will be automatically renamed for all the other objects. And this is because these two objects share, these objects all share the same two materials. So for example, let's use ITU marble for the wall and ITU metal for the roof. We can also set the properties for rendering. For example, let's use a darker color for the roof and maybe something like this for the walls. And as for the ground plane, these two materials, ITU marble and ITU metal, are baked in Sionna, ITU metal here and ITU marble. And therefore these properties would be used for simulating the interaction of EM waves with these objects. Once we have assigned radio materials to every object in the scene, we are done with configuring our scene, with setting our scene. One last thing we need to check is that the lighting of the scene is correctly set for rendering. To check this, go on the World Properties tab and ensure that the color is bright enough for rendering. Let's pick this color, and that the strength of the light is also high enough. This will do it. Once this is done, our scene is ready to be imported in Sionna. But to import the scene in Sionna, we must first export it from Blender as a Mitsuba scene, as this is the file format that is supported by Sionna. To do that, let's go on File, then Export, and if the Mitsuba Blender extension was correctly installed and is enabled, you should have the Mitsuba option available. Let's click on it. Blender will actually export an XML file and a folder named meshes that will store all the meshes that make the scene. Actually, there will be at least one mesh per object in the scene. To store all these files, let's create a folder and let's call it test scene here. This file will contain and let's store the files exported by Blender that will be exported by Blender in this folder. Before exporting the scene, we need to ensure that the coordinate system is correctly set, and that is Y forward and Z up. Actually, if you set Y forward, Z up will be set automatically. We also need to ensure that the IDs are exported, that is, that the names of the materials and objects are exported. And this is important because recall that Sionna uses the names of the material to assign EM properties to them. So we need to make sure that Blender will export the names of the material. Once this is all set, we can export our scene. And voila, you are now ready to import the scene in Sionna. We will now switch to the browser and open a Sionna RT notebook to import this scene. Let's now use Sionna to compute and visualize paths and coverage maps for the scene we have created in Blender. First, we import the modules we need, which includes Sionna with version at least 0.14. Next, we load the scene. We have put the test scene folder that contains the scene we have created in the same folder as this notebook. We need to load with Sionna the name of the XML file that was generated by Blender. Let's now have a look at the first 10 objects of the scene. Note that even this small scene contains already a lot of objects, and we stop after the first 10. For each object, we print the name of the objects and the name of the radio material that is assigned to this object. The first object is the ground plane, to which we have assigned the ITU concrete radio material. The other objects correspond to the buildings that were imported from OpenStreetMap. We can see that for each building, 2 meshes were created, one made of ITU marble for the walls and one made of ITU metal for the roof. This is not surprising, as this is what we have set in Blender. Next, we create a transmitter array and a receiver array. The TX array here is used by all the transmitters in the scene, and similarly the RX array here is used by all the receivers in the scene. The transmitter array is set to be a 4x4 array with the 38901 pattern, and the receiver array has a single antenna and uses the isotropic pattern. We also create or instantiate 2 radio devices, one transmitter and one receiver. For both radio devices, the first input is the name of the device, the second one is its position, and the third one its orientation. To get meaningful positions for the devices, we can use Blender. In Blender, select the cursor tool and then the View tab in the sidebar. You can then get the coordinates of any point in the scene by just clicking on it. For example, if we want to position the transmitter here, we just click there, and then we can read the coordinates in the view window. For example, we will position the transmitter at -43, 23, and 25. We use a slightly higher elevation to avoid that the radio device collides with the planes that models the roof of the building. So -43, 23, and 25. -43, 23, and 25. For the receiver, let's put it right here, for example. So -34, 53, and let's say 1.5 meter. -34, 33, is it 33? No, 53, and 1.5. Once the scene is set, we can compute a coverage map, and this is as simple as calling the coverage map function of scene. Note that the coverage map is computed using ray tracing, and we compute one coverage map for every transmitter in the scene. In this case, we just have one transmitter, so a single coverage map is computed. The computation of the coverage map using ray tracing is quite fast, as this is accelerated using NVIDIA's GPUs. Once the coverage map is computed, we can open a 3D interactive viewer by calling the preview function. Moreover, if we specify the coverage map as input, then the coverage map is also rendered as an overlay on the scene. For example, here in this window, we can visualize the transmitter and the position and the coverage map. So the transmitter is located here and the receiver is here. Note that by default, the coverage map has an elevation of 1.5 meter, and that's why the receiver appears to be in the coverage map. Once we have found a nice view point for rendering the scene, we can get a nicer rendering by calling the render function. The first input of this function is the name of the camera, and using preview the viewpoint of the preview window or the camera of the preview window would be used for rendering. Moreover, if we also give as input the coverage map, it will also be rendered. Note that this render function computes a visualization using ray tracing, and this is also quite fast as this is GPU accelerated. The coverage map is always rendered in dB, and when calling render, by default, a color bar is added to the figure. Such a rendering, for example, could be used in a research paper. Next, let's compute path. So this is also quite simple. All we need to do is to call the compute path function. This is quite fast, and this is done using ray tracing. Once we have the path, we can, for example, compute channel impulse responses. This can be achieved by instantiating a path to sear layer and then calling path to sear on the computed path. The output of this layer are the channel coefficients, which are complex values, and the delays, which are real values for every path. We can visualize the channel impulse response with the delay here in nanosecond and here the amplitude of the path. And such channel impulse responses could be used with the other components of Sionna to carry out, for example, link level simulation. So for example, we could use the SIR2OFTM channel function from the channel module of Sionna to compute the frequency response of the channel, which can be used to carry out link level simulations. We can also use the 3D preview to visualize the path. So this is achieved by giving as input to the preview window the paths that were computed. We can now see the transmitter, the receiver, and the paths that were computed by Sionna. Note that here, because we didn't give the coverage map as input, it is not visualized. If we want to get a nice figure, for example, for a research paper, we can then call the render function. And in this case, we have selected also the preview camera, so this viewpoint will be used. And as we give as input the path and the coverage map, both are visualized here. We have the transmitter, receiver, and the path. Okay, so this concludes this live demo. Let's recall some important tips for when creating scenes with Blender for Sionna RT. First, overly complicated objects, that is, objects with many triangles, should be avoided as they introduce extra compute and latency without necessarily adding value to the wireless propagation simulation. Secondly, always remember to correctly set the orientation, that is, Y forward and Z up, when exporting scenes. Also, when exporting scenes, remember to always export the IDs. Finally, use names for materials that are defined in Sionna RT, which is the case for materials that are baked in Sionna, that is the ITU materials, or custom materials that you have created. To summarize, here are the main steps to import a real-world environment using OpenStreetMap. First, import the area for which you want to carry out simulations into Blender, and add a ground plane if necessary. Then, assign radio materials to the objects forming the scene. Finally, export the scene as a Mitsuba scene and load it in Sionna RT. You can then use Sionna to compute and visualize coverage map and path and carry out link level simulations using the path you have generated. To deepen your knowledge and skills with Sionna RT, a white paper is available that introduces Sionna RT, as well as a primer on electromagnetics and a tutorial on ray tracing. All these resources are available on the website of Sionna. This concludes this video. We hope that you will find Sionna RT of interest for your research. To install Sionna, all you need to do is pip install Sionna.